Good morning. My name is Malihi. I'm a senior consultant with Fargol Research Group. This presentation is about surface active agents. We'll discuss basic points and principles of surface and colloid chemistry. And then we'll talk about the structure and property of surface active agents and their application properties in improving wetting, foaming, and detergency. And finally, we'll conclude with major surfactants in commercial use and new developments. Here's the outline of our presentation. This will be presented in 4 parts: an introduction to colloid and surface science, surfactants, application properties of surfactants, and commercial surfactants. Okay, a brief on colloidal systems. These are systems in which one or more of the component has at least one dimension within the nanometer range. That's 10 to the minus 9 meters range. These are extremely small particles, and they include large molecules and small particles. Examples are emulsions and suspensions, latexes, colloidal dispersions, micelles, and microemulsions. Key characteristic of colloidal systems are, because of the large surface to volume ratios at the nanometer range, the interparticle attractive and repulsive forces become very important. Surface active agents have profound influence on surfaces, and particle size, shape, and surface character become very important. Here's an example, magnified example of a colloidal dispersion of a pigment, and you see particles of various size and shapes here that are dispersed in an aqueous or a non-aqueous medium. We're able to detect these colloidal particles using the Tyndall effect and basically monitoring the turbidity to determine their concentration. A few points about surface and interfacial tensions. Schematic here, we're looking at an interface between a liquid and air. The molecules at liquid-air interface or liquid-gas interface are known to behave differently than those in the bulk. The reason for that is that the molecules in the bulk are under the influence of all molecules around them, so the forces are symmetrically applied around to this molecule or particle, but at the surface or interface, only in one side there are influenced by attractive and repulsive forces from the other particles. Therefore, these molecules are under asymmetrical force field, which produces surface and interfacial tension. Surface tension is defined as the energy to expand a surface of a liquid by unit area, or a force to expand the surface by unit length. It is a force acting normal to the surface and tends to reduce surface area. This phenomena of surface tension manifests itself here as you see the water beads on a plant that take a spherical shape. They tend to minimize their surface area. Similar effect with careful placement of a needle on the surface of water. We can actually float this on top of the water, and due to the forces of surface tension, this thing can actually be placed at the surface without sinking. Certain insects make use of this property by skating on top of ponds and lakes. Here are some surface tension values for different liquids. As you see, for water, surface tension is 72.8 millinewton per meter, or 72.8 dyne per centimeter. This is significantly higher than organic solvents like benzene, acetic acid, acetone, carbon tetrachloride, which are all in the 20 to 30 range. Ethanol is 22.3, and there are also some values here shown for interfacial tension.